want to talk now about proving identities, which is different than what we've talked about so far, which is verifying. Verifying, remember, means a numerical or a graphical approach to try to get a feeling as to whether one thing is equal to another. So for example, if I verified numerically, I would take a value of the angle and plug into both sides to see if I got the same value, and if I did, that would give me a feeling that maybe these two things are equal. Okay? The graphical way to verify is to plug each side into the graphing calculator and get two graphs, and if those two graphs are identical, that's another way to get an idea, a feeling, an inkling as to whether two things are equal or not. But verifying doesn't prove. To prove, this is what we need to do. We need to use known identities, identities that we've developed from core principles, and use those along with various algebraic techniques to show independently that each side of our equation is in fact the same as the other. We have to verify that the left-hand side is equal to the right-hand side, and we need to do this algebraically. So let's jump into a proof here and just talk about how it goes. What I'm asked to do here is to prove that this is equal to this. At the moment, we don't know that these two things are equal. The point is to show that this is true. And what we often do is we draw a line down the middle just to say that I'm going to work with this side independently, show it's one thing, work with this side independently, show it's another, and if I can show that the two things independently are the same, then I've shown that this statement is true. So the first thing I'm noticing on this question is that this right here, 1 minus cosine squared, is one of my core Pythagorean identities. It's sine squared plus cosine squared equals 1 rearranged. So this is equivalent to sine squared, so I can make that replacement. That's about all I can do on the right side, so I'm going to go over to the left side. So the question is, what do I do? How do I do this? Well, lots of different things you can try. One thing is you can convert everything into sine and cos, and I like to do that especially when I'm dealing with a product of quantities, as I am here. So that tangent, I know I can write as sine divided by cos, multiplied by cos, all divided by 1 over sine, because that's what cosecant is. So I converted all my terms to sine and cos. And one thing that often happens with that is that cancellations result. Well, I know that I can cancel the coses there because I'm multiplying the two fractions. And so now I'm left with sine x divided by 1 over sine x. And so I'm dividing two fractions so I can multiply by the reciprocal, and I'm able to show that the left side is sine squared, the right side is sine squared, and so I know that this statement is true for all values of the variable where the expression is defined. Alright, here's another question. So let's just put our line down the middle just to separate both sides. Again, lots of different things you can try. You need to try lots of questions to get comfortable with this. What I'm going to do on the right is I'm going to convert both of these statements to sine and cos. So secant is 1 over cos. Tangent is sine over cos. These are all identities I'm using that I have previously established. And so I have a common denominator, so I could write that like so. Okay. Not sure what more I can do on the right, so let's take a look at the left. Now, one thing that you want to keep an eye out for is when you've got a binomial denominator, what you can try to do is multiply top and bottom by the conjugate of that denominator. Remember, the conjugate of a binomial is the binomial with the opposite sign in the middle. So I'm going to multiply numerator and denominator by 1 plus sine x. And of course I can do that because 1 plus sine x over 1 plus sine x is 1. 1 times my original expression doesn't change anything. So in the denominator I'm going to multiply out, just like algebra. Okay, 1 minus sine squared x. And in the numerator I'm just going to leave things in factored form. Okay. Now 1 minus sine squared x is my core Pythagorean identity rearranged. Sine squared plus cosine squared is 1. So 1 minus sine squared, this is cosine squared. And so I make that replacement, and then what I can do is, since we have factors on the top, I can reduce one cos with one cos, and I have shown that the left side is equivalent to the right. Continuing, just to try to show you some of the different techniques that get used with identities. In this particular one, again, let's just draw our line down the middle. We've got to independently show that both sides are the same. By the way, you can't move terms from side to side. You can't do that, because you can only do that if you know these things are equal. We don't know they're equal. That's what we're trying to show. Okay, so you work independently with both sides. Okay. On the left, this is reminding me of something like having x to the fourth minus y to the fourth, which is reminding me that something like that could factor as x squared minus y squared, x squared plus y squared. So in this case, I'm going to factor this expression. You'll notice how various algebraic processes get applied to trig when you're proving identities. Okay, and how does that help me, or does it help me? Well, it does, because this factor, sine squared plus cosine squared, we know that's 1. That's our core Pythagorean identity. So 1 times the other bracket is sine squared x minus cosine squared x. Alright, so if I take a look at the other side and look at how I'm doing, I'll notice that I'm getting closer to this side, but this side doesn't have a cosine squared, so maybe I need to work at replacing this cosine squared with something involving sine squared, and maybe the two will end up being the same. Okay, that's kind of the thinking process that has to go on in your mind as you're trying to problem solve your way through this. So I'm going to take my core Pythagorean identity, sine squared plus cosine squared is 1 again, and I know that cosine squared is equivalent to 1 minus sine squared. I'm going to do that replacement, because that's a known identity. I can then distribute my signs. And sine squared plus sine squared is 2 sine squared, which is identical to the other side. And so I have proven the identity. Another identity. What I'm going to try in this one is I'm going to multiply the right side out. So I've got a plus b squared. I know how to do that. Square the first term. Multiply and double. So that would be 2 tan x cotan x. And square the last term plus cotangent squared x. Alright. Do I see anything that I know to be true? Well, one thing I notice is that tangent times cotangent, these are reciprocal ratios. Cotangent's 1 over tan, so tan times 1 over tan would be 1. So I can replace that middle term with 2 times 1, 2. Now, you've got to be constantly thinking about things you know, identities you know, that perhaps will make this all work out. How am I going to equate what I have here to the left side? Well, you might remember that we have identities involving secant squared and tangent squared. If you go to your identity sheet, you will find an identity, one of the Pythagorean identities, in which secant squared is 1 plus tangent squared. So I can make that replacement. That's a known identity. And you'll also notice that cosecant squared, another Pythagorean identity, is 1 plus cotangent squared. And so if we combine our 1's, we have reduced the right side and the left side to be identical. And so we have proven the identity. One more example. I'm just trying to show you lots of different techniques that get involved, and there's lots more that you will figure out as you problem solve your way through this. A more complex looking expression. So the question is, what am I going to do? Lots of things might come to mind, but for me, what I notice is that when I see tangents and cotangents, the common thing that they all have in common is they're all related to tangent. So I'm going to change all the cotangents to 1 over tangents. Alright, and what I have now is I have little mini fractions within the larger fraction. That's what I call a mini fraction within the bigger fraction. They're called complex fractions, actually. And what I'm going to do is, to simplify those complex fractions, I'm going to take my expression and I'm going to multiply top and bottom by the common denominator of those mini fractions, which is tan x. Okay, I'm going to do the same on the other side in a minute. I'm going to multiply through on the bottom because that will eliminate my mini fraction. So I'm going to get tan x plus, multiplying these two, the tans cancel out to be 1. On the numerator, I'm not going to multiply through. I'm just going to leave it in factored form. And you might say, why did I do that? Because this package here, this unit, and the unit on top, they're common factors, so they can reduce. And so I've reduced the left side to tan x. Alright, let's see if I can do a similar thing with the right side. So I'm going to multiply top and bottom by tan x, which is my common denominator of my mini fractions. So on the numerator, I'm going to have tan x. I'm going to leave it in factored form. And distribute. That's going to be 1 minus tangent x. That's a unit, as we know from our study of rational expressions previously. And so that factor cancels that, and I've shown that both sides are tan x. And so I have proven the identity.